Okay, so correlation, simple regression. Everything we've dealt with so far is we're talking about looking at differences between means, really group differences. Right? That's t-tests, z-tests, analysis of variance. They've all been the same way. You can actually look at this from a somewhat different angle, which is that it's a relationship between independent and dependent variables, right? The independent variable, what you vary, dependent variable, what you measure. You can look at it as a relationship between those two. Now, sometimes that relationship, sometimes the independent variable is actually a quantitative thing, right? Like if it was a retention interval, which I've used quite a bit, will have so many hours in it, or so many minutes in it, or whatever. And we can then look and see that, for example, as time goes by, memory, number of words recalled drops. So you're talking about a relationship there between an independent and dependent variable. But this could also be true of qualitative variables, right? Male, female, right? This could be true of, or I don't know, psychology students and biology students, or whatever, right? So a psychology student isn't more of a student than a biology student. Like it's not quantitative. You can't say anything about a number there. You can just say they're in two different categories. So you use categorical variables too. But you still say there's a relationship between major and what are we better at than them? Everything. I think they almost learn as much stats as you guys do now. Because I would normally say statistics. Usually psychology students, no matter where you are the best trained people in statistics other than people taking statistics as majors, which we don't have here. Oh, I don't know. Oh, I bet survey construction, which is something I don't think they use very often. And while you may not have a great deal of training in it, you have more than they do. But, okay, so we're better at that. And they're better at, I don't know what, naming plants. That's probably what they do. That's mostly what biology is, just naming plants. It's like geography is just coloring, right? That's what geography is pretty much. It's just coloring maps. It's colored pencils. You have to make sure you have the Laurentian colored pencils. I say that to William Osai constantly, by the way. So you cut and paste it today in class? Coloring? No, thank you. My impression of William Osai. Apparently it's not good enough to... Some of these are jokes, guys. I know it's late in the term. So again, you look at this as a relationship between the independent and dependent variable. Continuous variables, this is easy to see. That's the difference. So say psychology, biology students, it's hard to put something on the x-axis that's meaningful, because moving over to the right doesn't mean you have more of something. But with a continuous variable, or a continuous, or a discrete a quantitative variable has a lot of levels, it's pretty easy to see something. So if we looked at something like a scatter plot, which is something that's great for exploratory data analysis, and we looked at, if only this were true. It is to a point, by the way. Your IQ score and your salary actually do correlate quite highly, not that tightly. Right? I think when I made this, I just put in a bunch of numbers and then I told my spreadsheet program to make a graph. So, and obviously, it's not that kind of correlation. That's like about a 0.8 correlation at least, and it's not. There's no way it's that high. It's about 0.5, which is pretty high. Right? So okay, that's IQ and income. It's not really. It's not. Again, it's not that tight. You'd see a positive relationship, but it wouldn't be so tightly packed. Okay. Move that over. So, and the scatter plot itself is a useful EDA tool, right? Exploratory data analysis. You just look at that as a relationship. Like, you can look at this, everybody can see this, one goes up, the other one goes up. It's really easy to see. Right? We need a way, though, to standardize the variable relationships and to see if they have, even if they have different scales. And of course, IQ is, I don't know, it's IQ points. And this we'll say is income in thousands of dollars per year. So they're they're measuring two entirely different things, but we want to be able to say there's a relationship between one and the other. We want to be able to say that your IQ, if it's measured by the WACE or the Raven Progressive Agency Scale, and your income, if it's measured in Canadian dollars or euros, it doesn't matter. We want a way to be able to say this, and we get the same number at the end. Okay? That's what we want. So even if they have different scales, and they almost always do. Okay. One way to start this is something called covariance. The covariance of x and y, that's how much variance two things share, how much two variables covariate. And at first you look at that and go, what the hell? But think about this. This is think about what a variance looks like normally. It would be the sum of x minus x bar squared over n minus 1. It's variance, yes? Okay, so that's what variance is. Covariance just has the x minus the x bar, and then y minus y bar. So if you're so far off from x bar, how far off are you from y bar? It's how much two things come together, in which they covary. So it does look a lot like a variance formula, doesn't it? It's just that here, this is a covariance formula. Okay? This is the covariance of x and y, not the variance of x or the variance of y. So it's not an incredibly complicated formula because it looks a lot, it's basically a variance that's using two variables. And this measures the degree to which two variables vary together, how much they co-vary, hence the name. If deviations from x bar and y bar go in the same direction, you get a positive covariance. You can also get a negative covariance. This is the difference between a covariance and just a plain old variance. Variance is always going to be positive because it's a squared quantity. This has two numbers multiplied times each other, except one could go one way and one could go the other. What's something where one goes up, the other one goes down? You think of a variable where one goes up, the other one goes down. Let's see. I bet if we looked at latitude and population density in Canada. Yeah. As the latitude goes up, the population density goes down, doesn't it? Right? There's parts of the Northwest Territories where people just go, I'm not going to live there. Why would I live there? No one wants to live there. Right? There's the odd little community, that's about it. There's that Canadian Forces Station at Alert. Have you ever seen that place? It's the furthest north anywhere it is. I knew somebody who worked there, and it was the only Canadian government building where you had to smoke inside. They said because if you smoked outside, because what happened with gasoline, with whatever leak, it just sat in the snow and never evaporated, and you could just light the snow on fire from all the vehicles. I don't think you probably just let it smoke at all there anymore. Okay, there's places like that, but for the most part, population density is really small. So if you're below the average latitude, this is going to be negative. Above the average population density is going to be positive, and then we end up with a quantity that's negative. On the other hand, we can think it's very easy to think of things there as one goes up, and it goes up height and weight. Right? Usually the taller you are, the more you weigh. Okay. I remember we're summing all these, so sometimes we're going to get strange cases. Sometimes there are going to be people who are 7 feet tall. Not very many, but there are going to be some. And they weigh 180 pounds. There's not very many of those guys. Right? If you think about North America. By the way, in North America, if you are over 7 feet tall, there's a 16% chance you actually play in the NBA. That's how few people there are who are over 7 feet tall. But I can think of one guy who used to play in the NBA. who was from Somalia. He was 7'10", a guy named Manute Bol. And when he came to the States to play college basketball, when he was recruited, he weighed 160 pounds and he was 7'10". Now, he just drank milkshakes like all the time to gain weight. He eventually played in the pros. Holds all kinds of records with shot blocking because people take shots and he goes, no, I don't think so. No, I got that. Oh, no. He didn't have to he didn't have to jump to dunk. And he was a really sweet man. He did all kinds of things for Somalia. He died recently. It's really sad, actually. But he would be a case you go, well, his average weight is low for his height, but most of the time when you're 7 feet tall, you also, even if you're all muscle, you might weigh 280. Right? So on average, you're going to end up with a positive number for covariance in that case. At some point, look up Manute Bol. It's spelled just like it sounds. B-O-L is how he spells last name. It's crazy. Watching him play because it looked like he was just so thin, even though he was fit up to about 210. Like he still weighed a little bit more than me. He was like, no. He got good at 3-point shooting, which is kind of great. You sort of think he's big, by the 3-point line. There you go. No, he wasn't quite that tall. It was close. So we want a measure that isn't just covariance. We want what's called a measure of association. We have to standardize covariance because think about it. If we were measuring height and weight, and we were doing the height in centimeters, rather than say inches, but I was using inches because most of us still, even though this has been a metric country since 1974, anybody here know their height in centimeters? You actually know it? Okay, 1, 2. Your driver's license or are you in the Army? Okay. The only people usually that know it are people that they've looked at their driver's license recently or they're in the military. That's who knows what they weigh in kilos. I don't know. I'm just confused. They changed our system when I was in grade 4. So I was learning feet and inches and pounds and all that stuff. And they went, that's all bullshit. Okay, centimeters and kilograms. I'm like, I don't know. So I'm just confused. People at my age are just confused generally with measurement. Temperature outside, 7 Celsius. The temperature of my sister's pool, which is a long story, this house I grew up in, that's done in Fahrenheit. I don't know why. Very, very confusing. Distances in meters and centimeters, except if I'm doing something like, measuring something. Then I'll say, okay, that's 6 5/8. I don't know how many centimeters that is. But if we did it in centimeters, the number's going to be bigger because it's about differences from a mean, and just the numbers are, there's more demarcations in centimeters. We want something where it doesn't matter if it's in centimeters or if it's in inches or if the weight is in pounds or kilos or stone, as they use over in the UK. How much do you weigh? Oh, 3 stone. I don't even know what that is. That's not much, right? I think a stone is 14 pounds. So if you weigh 3 stone, you're pretty thin, or you're a small child. I weigh 3 stone. That's my British kid who weighs 3 stone impression. I weigh 3 stone. Go down to the pub. So covariance is going to depend upon the variance. If it depends on s sub x and s sub y, let's divide by s sub x and s sub y. Right? That's what it's standardizing. That's the way, so if we have this measure in pounds or kilos or whatever, we can say, doesn't matter. We get a number. So that's what we're going to do. It's got a name. It's the Pearson R. The Pearson product moment correlation coefficient is, I believe, the technical term. So we take the covariance of x and y, and we divide by s sub x times s sub y. It's named after former Canadian Prime Minister Lester Pearson. Oh, he isn't. I just made that up. Named after a guy named Pearson who figured it out. It was not Lester Pearson. Too bad it wasn't. That'd be great. On the side, won the Nobel Peace Prize for inventing UN peacekeeping, Prime Minister of Canada, leader of the Liberal Party in the 1960s. Oh, and also invented a statistical procedure. Too bad that's not true. But tell people that. So if the covariance, the absolute value of the covariance of x and y equals the standard deviation of x times the standard deviation of y, then r, the absolute value of r, equals 1. And you have, why there's 2 a's there, I don't know. Been watching a lot of Norwegian television lately. Maybe that's why. It's got subtitles, so it's a great show. Occupied on Netflix. Oh, baby, what a show. It'll be a perfect relationship. So your height in inches and your height in centimeters. It's going to be, it's a straight line. You know, covariance of whatever, and the multiplication of the variance of the two is going to be the same. It's going to be 1. Yeah? So how much they covary, if it's the same as how much the two variances multiply together, that means they're both measuring this exactly the same thing. Right? Those of you who've taken neuropharmacology know that the closest thing we might come to this in sort of psychology is the effective dose of the ED50 for antipsychotics and their D2 receptor binding efficiency. It's pretty much a 1.0 relationship. The only piece of data I can think of offhand. The sign, though the sign can vary, see, because these two standard deviations are going to be positive, both of them. So there's a positive number here. Can't have a negative number here. The sign's only going to indicate the direction. Positive, negative. Right? Positive is it's going uphill, negative you're going downhill. That's all that says. So when I ask you which correlation is bigger, I've used this in the Stat 21-26 quiz. Back when last time I taught that was a long time ago, but it was 09 maybe. You know, if you had, I think the question goes Kenny, because I always name people Kenny in my questions. Kenny calculated 3 correlations. He found negative 0.7, positive 0.4, and 1.2. Which one's bigger? And the answer is negative 0.7, because 1.2 is in a correlation. It can't be bigger than 1. And the sign doesn't matter, it just tells you direction. Okay. So negative 0.7 is a bit higher correlation, tighter relationship than positive 0.4. The sign just tells you the direction, that's all it does. R can only be between negative 1 and positive 1. It can't be greater than 1. If it's greater than 1, you did it wrong. It's literally, look at the formula. It's impossible for that to happen. This quantity, the covariance, how much two variables vary together, can't be more than how much two variables could vary together if they all vary. No, it's impossible. Can't be done. It just can't be. You made a mistake. Now, frankly, no one calculates this stuff by hand. So if this comes out, if you use Excel or any other Google spreadsheets, numbers, Mac program, it doesn't matter what, you can do a correlation coefficient really easily. Right? If somehow it comes out to a number greater than 1, it won't. It'll just say error. You made some kind of mistake, whatever. If somehow, if you were doing it by hand, maybe you have 10 numbers and you just feel like doing it yourself because you're, I don't know, a freak. You did it right. You know how easy this is to do in SPSS? I'm not even going to show you. 2 columns of numbers. Pick correlation and say what the 2 variables are. Done. You can do that, but you can also do it in Excel. Select the 2 things and say equal. Select the cell equals correl. Open bracket. 1 data. 1 column. Column other thing. Other column. Close bracket. Equal integers. There it is. That's how I know the correlations of what your test marks are, because I always report those things. So it can't be greater than 1, it can't be less than negative. But remember, the sign only indicates the direction of the relationship. Oh, it's also straight lines only. I mean, there's no, you can't, like here's a great, here we go. And let's say we have, you know what? Think about a dose response curve in pharmacology. Low dose, not much effect, and then low dose, and then right in the middle, you get sort of a sweet spot, like that, we get something that looks like this. So that, if we could draw a line, it was perfect, like that, like an upside down parabola. You know what the R is for that? It's 0. It's 0. Except that there is a nice relationship there. It's a perfectly beautiful relationship, except it's one that R can't measure. R needs straight lines. It only works for linear relationships. They're like curves. Okay? So there's a lot of things in psychology generally, like the Yerkes-Dawson law, right? You have arousal and how well you do on some task. Mid-level of arousal is good, too low, you're asleep too much, you have a panic attack. Somewhere in the middle to this. Right? There are ways to analyze data like that. There are correlation coefficients that use R, so they're exactly the same, except they don't. This thing assumes a straight line. One of the assumptions of the math here is a straight line. So instead we assume a parabola, let's say, and go from there. That's easy to do. It's totally doable. Okay. So it's got to be a straight line. It's got to be a straight line. We should be able to predict y from x. So if we have your x, we should be able to say, what's your y supposed to be? Right? And this is one of those things. You guys have kids? Because when you take your baby in the first few times, the doctor, you go like every month when they're first born, and they weigh the kid, and then they measure the length. Can't really say height yet because they're not standing, they're long. So, and they say, okay, the weight looks good. And they look it up on a chart. And in fact, what they've done is they're predicting the weight from the height. And if it's too low, if it doesn't work, they have an equation. And, well, you should probably, I don't know, give the kid some butter. That's probably not what they say. Apparently my mom was too thin. This is, of course, 1946. So the doctor said, I don't know, give her some condensed milk. I love the 40s. Probably had a cigarette going when he was talking. I'm sure my grandmother did too, but be nice we can predict what next. Obviously we can, or those doctors couldn't do that, or just be making stuff up. It's like, I don't know, kid looks fat. I mean, what a skinny, scrawny little kid you got. Give him, I don't know, milkshakes. Here's a bottle, that'll be good. Kid's fat, give him some amphetamine. It's the 40s. It's my doctor in the 40s prescribing amphetamines to children impression. Rarely used. Never. I just pulled that out right there. Never going to use it again. Not funny. So we're just drawing a line through a scatter plot. So yeah, we can do that. Sure. Okay. So scatter plot. We can do it here. Take the scatter plot here. Here we go. VP again. Okay. So here's some lines, or dots rather. Lines. Okay, those are good. Okay. So let's see. We can draw a line. That looks pretty good. Sure. That looks good. It's hard to choose between those two. Actually, those are both pretty good. What about that was good. Sure. What about, now some are going to be really lousy. Like we all know it seems to go up, right? So this one would be no good. You could draw that line and say, that's a stupid line. It's exactly the opposite. It's a stupid line. Your lines are stupid. Because it's going exactly the wrong way. Because it looks like as one goes up, the other goes up, and we wouldn't have like the negative slope. That's dumb. Or we could, here's another line we could draw. I don't know. Well, that's also stupid. It's saying there's no relationship. We see a relationship. We could draw this one. Just connect the dots. But now you're doing what's called exhausting the degrees of freedom. What you're doing there, in fact, it's a perfect prediction, but it's a useless prediction because I need all the data to make a prediction. That's a useless line. So, well, probably one of those first three that I drew before I got ridiculous there, is probably the best one. Question is, how do we do that? So we have to draw a line through a scatter plot that's going to do a nice job predicting. We want it to kind of over-predict as much as it under-predicts. Okay. So this is what's called the least squares regression line. The least squares regression line. It's a way to pick a line that we can all agree how we've done it. That's all that's happened here. So it looks like this. So here are 4 dots, 4 data points, and here's a line. We've got, these are actual y's. These are correct, by the way. Y hat, as this is called. It's called y hat, which is really weird. It's like it's got a little hat. It looks like a circumflex to me. I keep wondering, I wanted to ask friends of mine who teach stats and also speak French if they call it Y chapeau, Y chapeau, or they call it Y circumflex. I kind of hope it's that. I kind of hope it's avec un chapeau. Y avec un truc là, something like that, like a sort of a Quebecer way to go.
Might just call it Y hat.
Or maybe just Y hat, yeah. Regarde ça, c'est le Y hat, là. Like, no, they're not doing that. That wouldn't work. As you can tell, I don't speak Parisian French, I speak Quebecer French. So much for Quebec, that's what I learned. I speak impeccable hockey French as well. So Y hat, Grec chapeau, it's wrong, because these are right. The Y's are right. These are errors. These are prediction errors, right? This is under-predicting, these two on the top, and these are over-predicting. But you see what it's doing? It's over-predicting as much as it's under-predicting. I've got to remember to ask Sylvain. I've got a buddy, Sylvain, who teaches at University of New Brunswick at Edmundston, and he's I see it every conference. I always forget. I can email him. I almost feel like I'm doing it right now, but I'm not going to do it right now. I will today. Someone remind me. I really want to know. Good. Overprediction, underprediction. Want to overpredict as much as it underpredicts. So what we do is we minimize these differences. We've got to come up with a line that makes those prediction errors as small as possible. Okay? So we want to minimize the sum of y minus y hat squared. We're minimizing the sum of squares. And you guys remember this. You may not remember how to do minima and maxima of functions because it's been a long time. But you probably remember that it wasn't that hard to do. Right? It was one of those things, it's like, what's the minimum, what's the maximum? Mathematically, it's not a complicated thing. You probably did it about grade 9 or grade 10. Maybe even before that. Right? So it's something you know that you remember. You might not remember how to do it, but you can say, oh, yeah, it's certainly doable. Right? So we want to minimize the sum of the y minus y hats. In other words, we want to minimize the prediction errors, or what are called residuals. So we end up with what's called a prediction equation, or a regression equation. It's y hat equals a plus bx. Y hat is the predicted y. A is the intercept, and b is the slope. And you're going to say, Dave, I was taught that y equals mx plus b, and m was the slope, and b. I know. Look, I don't start this. Don't blame me. A is the intercept, b is the slope. So you end up with this. I'll show you in a second how to calculate. Again, this is something, it's so easy to do with something like SPSS. You just choose regression and say what your independent variable is and your dependent variable, and it'll just give you a regression equation. And it happens instantaneously. Oh, well, almost instantaneously. Okay? Not so bad. And as annoying as it is now, because you all learn y equals mx plus, they still teach that, right? Y equals mx plus b when they talk about linear functions. Yeah. Well, go back in time and tell your grade 11 math teacher that he screwed up. No, we didn't. That's how they do it in math. This isn't math, it's statistics. Y equals a plus bx. A is the intercept, b is the slope. Slope of the line. So b is going to have a sign, negative or positive, and it's a coefficient, right? Because it's multiplied times a variable. X is a variable. Oh, if you want to calculate, here's how you do it. No one does this by hand. This is done by hand if someone's being mean and they're running out of ideas about how to give you assignments in an intro stats class. That's when you do these by hand. In other words, that's exactly what I think was happening when I was in second year stats. Because why would you do this by hand? It's ridiculous. No, it's not that bad. Covariance of x and y divided by the variance of x. That gives you b. And your slope is y bar minus b times x bar. So you see, once you find b, it's easy to find a. And this is where you see covariance divided by the variance of x. This is where you're going to get the sign in there. Positive, negative, right? It's not something you, like I said, no one calculates this by hand, but if you're wondering how to figure it out, there it is. The question is, how do we interpret this? That's the important thing. Because you end up with an equation. So it's something like this. So we have y hat equals a plus bx. Now, wouldn't it be nice if we could predict someone's salary, right, as a professor at Algoma University, based on how many years they've taught here, right? In fact, that's how our salaries are calculated, okay? So it's the number of years, which varies from person to person. Oh, it looks like x. Times some constant. I'm simplifying it a little bit, but it's basically this. So let's say it's about, and we'll leave this in thousands, 3.5 times x plus, now there's a base salary. When you start, you're not paid zero. It's not like you have to work for free. It felt like that for years, believe me. When I started here, my salary started with a 3. And it didn't have 6 figures. Let's put it that way. That was 1996, a long time ago. Yeah, I made $3. That's what it felt like. My family subsisted on nothing but gruel. I mean, I had drinking money, but family money's different. So I don't know. Base salary, assistant professor, is about, it's probably that. Yeah. I don't actually know because it's not I'm not an assistant professor, I'm an associate professor, but it's something, it's close to that. So then you can look at that and say, okay, what would someone make if they have taught here for 10 years? Yeah, so this isn't actually totally accurate. But if we did 70 plus 3.5 times 10, it would be 105, right? So 105,000. And that may not be that far off, actually. So you see, the idea of what this equation is just, whereas it's not a regression equation with our salary scale, because there aren't people that vary from it, you're on the line. If you're not on the line, someone in HR made a giant mistake. Right? Happened to be what's in Newfoundland. It's like, you're underpaying me. And we're not, yes you are. I can do arithmetic. Yes you are. It took 4 months. And they finally went, oh, sorry, we've been underpaying you. I know. I told you. Can I have the money you owe me in interest, please? Oh, that much. I don't care. It's a principal thing. I want the interest. So I got the interest too. It's like $8 or something. It was really nothing. So it's that kind of thing. It's the same thing that the doctor is doing when looking at your babies and then looking at a chart. Yeah? Spit a little bit there. Horrible. Spit some coffee. It's gross. Anyway, I'm glad people on YouTube, you didn't see that. It's too bad because it was really something. Okay. So A, the intercept is where x equals 0. It's not really that meaningful. In this case, it is meaningful. In this case, it is meaningful. When someone comes here and that's roughly correct. I don't actually know. Because that's not, as I said, that's not the salary scale I'm paid on. But when someone starts, if they have no experience, 0 years of previous experience, they get the base salary. So in this case, with a salary calculation, it's actually meaningful. It's actually meaningful. Right. However, if we were looking at weight and height, right, so we're predicting weight from height. So y is weight, x is height. So it says here, if you weighed absolutely nothing, you'd be 3 inches long. Well, no, that's ridiculous. So you can't really interpret it in that case. That's obviously the weight of your soul. The height of your soul. Your soul is 3 inches tall. It wasn't meant to offend anyone. Though most things I say aren't meant to offend people, and I offend people constantly. Nonetheless, that would be a completely meaningless intercept, right? Most of the time, in fact, the intercept is meaningless. It's meaningful in the weird case that I've got here, the example of, let's say, how you calculate someone's salary. So you actually could literally go into the collective agreement, which is a public document, and you can see a thing, and then you can say how much money you can figure out all, if you know how long we've been here, you can tell how much money we all make. Very exciting, isn't it? I don't care. Some people are, who shouldn't tell people that? Well, it's a public document. So, it has to be a linear relationship. This, again, the salary scale thing is a linear relationship. As you go up, it goes up by a certain amount. It doesn't say once you hit 10 years, you get extra. It doesn't work out. Once you get promoted, you get extra. Then you go into a whole new intercept and a whole new slope. So it's linear relationships only straight lines. So the height and the weight thing tend to be straight lines, and if you look at, if we did a scatter plot, just even of all of us in the room, we would find pretty much a straight line. It's not going to be curved in any weird way. This shows the importance of exploratory data analysis. So a lot of times, and this happens to psychologists all the time, they do correlational work, and they pump out a coefficient, and they don't look close enough at the scatter plot to realize, in fact, hey, that's not quite a straight line. So you should be a little careful about that. One of the ways you can find out is you can look at the residuals. You can also look at the scatter plot, but you can look at the residuals. What you can do is plot the prediction errors. And that's an easy thing to do, again, when you're doing regression in something like SPSS. You can just say, I want to see residual plots. The residuals, if I was to do a plot of residuals, call them E for error. And then X on this axis here, and this is 0. They should look like this. There should be no relationship between X and E. In other words, as X gets bigger, the prediction errors don't get bigger, or they don't get smaller. There should be no relationship, or they shouldn't be like curvilinear or something like that. And you might think, why the hell would you do that when you can just look at the scatter plot? Good point. But next time, we're going to talk about not only having one X variable. We're going to have lots of X variables. It's going to be multidimensional, not just two. In that case, it gets a little hard to look at a scatter plot. You know, what's a scatter plot look like in 4 dimensions? Dude, mind blown. Right? That's hard to do. I don't even know how you. The paper goes to a parallel universe. It comes back and it's evil. You know it's evil because it has a beard. Parallel universe. Star Trek. Anybody? Spock? Nobody? Mirror episode? No? Okay. Sad. And Joey is obviously evil because he has a beard. I mean, I think we all know that. In the parallel universe, though, he doesn't have a beard.
Well, the Riker character's got a beard.
See? You ever watch Riker, how he gets on chairs? Have you ever seen those videos?
He kind of steps over this.
Steps over chairs. He gets on the chairs like this. That's how he sits down. And now that I've shown you that, said that to you, next time you watch Star Trek Next Generation, you're going to notice it, and it takes you right out of the show, because he does it all the time. There are videos on YouTube, just type in Riker chair, and you can see it's the weirdest thing. It's got something to do with he has a bad back, and he's like 6'4" or something. So that's how he gets on chairs. Gets on chairs, also sits on them. I think the technical term is sitting on a chair, not getting on it. Near the end of the term, I am losing the will to live. I don't know about you guys. So you look at the residuals, it's totally useful to do that. Again, right now with two variables, you probably wouldn't just look at the scatter plot. But once you get more than two variables in there, you're going to want the covariance of residuals and the residuals and the x should be 0. I mean, that's what that is here. There's no relationship. So you can actually calculate that if you want. One of the things you can't do, and it's very tempting to do this, because what this gives you when you actually make one of these regression equations is it says something equals something. It's telling you this is this. It's mathematical. So you're very tempted to go, well, that means then, obviously, if someone worked at the university for 200 years, why, they'd make millions. Well, you can't do that, right? A friend of mine, Todd, I've told Todd before, quite a few times, and Todd, one of the things that he did when he was in grad school is he was trying to predict how many cigarettes people smoked per day. Okay? And he did it using regression and a questionnaire. It was pretty cool stuff. But when you come up with a regression equation, you can't say, okay, cigarettes per day equals, and it's not this simple. It's a little more complex. It's actually 4 variables. But if it said something plus something times the maximum number of cigarettes it's smoked, you can't look at that and go, well, I see. Or even better, let's say it's age. This is no smoker, so it's age. How many cigarettes smoking? Age is one of the variables. You can't say, well, I see. So if someone is only 1 year old, they smoke this much. And yes, I know we've all seen smoking babies on YouTube, but which we all laugh at, and then we should be horrified by. But babies typically don't smoke. Or, no one's, so if you were 300 years old, you'd smoke thousands a day. No. So you can't go outside the range of things. It's so tempting. It's so tempting because you have something that says this equals this. You got to keep in mind what it actually says is this. I predict that if I put these numbers together, here's the prediction I'd make. That's all it says. It's not saying that you look at it. It's got x's and y's and equalses and pluses. That sounds pretty ironclad to me. Like, it really looks that way. It feels that way to me. I mean, to me it even does, and I know that that's bullshit, that it's not, it's a probabilistic statement you're making, and we'll talk next time about how to sort of test that probabilistic statement. That's the first thing. But secondly, you're also, it's from a very limited set of data. Even if it's thousands of data points, you can't say that, like I said, you can't, people are really tempted to go beyond the range just because it says equals. Mitch.
Just because of pure interest.
Yeah.
So the minimum salary for just anybody at the university using this formula would be A?
Yes. Not anybody. This would be only for faculty on a certain pay grade on assistant professor. Yes. Yeah, that's what that would say.
Yeah.
And that's probably roughly correct.
What's the maximum?
There are maxima for all four different pay grades, for lecturer, assistant, associate, and full professor. I offhand don't know what they are. I don't think I'm close to the maximum yet. I'm an associate, so I don't know which is the third highest one, or the highest one for full professor.
I'm not sure if this is an average or not, but it says 120. It says it's between 105 and 120K
For who?
for associate professors.
Here?
Yes.
It's more than 120. Where does it say that?
Glassdoor.
Oh, I can tell you from personal experience. It's more than 120. Yeah.
What?
No, you can look it up in the collective agreement. I don't know exactly what it is. But it's not a whole lot more than that, I don't think. Assistant's probably 110 or something. Yeah, and full's probably like 150. I think. But that's just a guess. I honestly don't know. I don't think I'm not at the ceiling yet. Which is good, because I like getting raises.
Yeah, assistant somewhere between 101 and 109 according to this.
Other questions? I know because I just do my taxes, so I know how much money I get last year. So. All right. So we'll stop this.